Alright, this will be the last video lecture for this section. We're going back to diffraction. When wavelength is much smaller than a slit size, when it's comparable to the slit size, then we get diffraction effects. And we said that's the bending around the corner, so to speak. Diffraction pattern is similar to the pattern we see for Young's double slit. It's interference, but the difference is it falls off much quicker in terms of the brightness. So the center one's really bright and the others fall away fairly quickly. The thing is that for the diffraction pattern, we get it even with a single slit. So we don't have to have multiple slits. The equations works out fairly similar. You start off with a single slit, and you talk about the different minima and maxima by looking at y. Set up a similar triangle to what we had before, but basically you divide the slit up into little pieces and they all interfere with each other. The math's a little more complicated to get out the pattern, but still we get lights and darks like you see here. I didn't give any problems that needs that. It uses that formula, but it's similar to what we had for Young's double slit. Now, one of the things is, though, it helps us understand why optical instruments, even the eye, which is a good optical instrument, if you want to go back and I didn't do a lecture on it, but back on the first, the same part that has the lenses, there's a set of slides for optical instruments, and it's in the book, and it talks about how the eye works. But there's a limit to what we can see in terms of size and distance because of the diffraction pattern. The diffraction pattern, if two diffraction patterns overlap, then we can see it. If they don't overlap, we can't. It's called the Rayleigh criteria. It's a little different when you're looking through a circular hole than a linear slit, but it's similar. The math's a lot more. But nonetheless, we get a pattern. And you can see this in a microscope or telescope. You can defocus a telescope and look at the diffraction pattern that you get for, say, something like the moon. And you can see those concentric rings. I think I've got a picture of one here. Yeah, here we go. That would be shot through something like a telescope. And so when objects are small, if their diffraction patterns overlap, you can see it's not just a point, but it's spread. If they overlap, we see it as a single object. If they're separate, then we don't. And when you work out for the circle and Bessel functions and all that good stuff, then you don't get a nice whole number, but you get that the minimum angle is a 122 lambda over d, where d is the aperture of the telescope, or the eyeball. So it's looking at diffraction patterns that let us figure out how far away can I see something with my eye or with a telescope. And there they are where you can't really distinguish them. The other thing for diffraction is we talked a little bit about diffraction gratings, and we took our double slit and we said you could expand it. The diffraction grating is usually a piece of glass or plastic with literally hundreds of small scratches, small grooves that have been cut in it, several hundred per inch sometimes, and it will diffract the light for the same reason you get the interference effect. And they usually pass one out and look through it, and that's what it looks like. You can look at a window, say, or a bright light, and you look to either side and you see the rainbow just like we get through the prism. And those are much cheaper. You know, a good prism that'll do that costs you hundreds of dollars, whereas a diffraction grating you can get for a couple of bucks. And there's a picture. You can predict where those are. And so that's how people study, for example, large molecules, that we will send X-rays, and the spacing in the atoms acts like the slits. And it'll give you some patterns. Now, it's three-dimensional, so it's really quite complicated, but you can do the math. That's kind of a specialty. But there's math that'll let you, knowing the spacing, the angles, and the distances between the brights, you can calculate back out what the spacing in the crystal is. It's called Bragg diffraction. And actually, the father-son team by the Braggs got Nobel Prizes for working with that. it was that type of thing. There's a pattern for a barrel crystal, and you can see it's very complicated. Actually, quite beautiful. Here's another one. And so you can imagine that it's very complicated to pull things out of that, but it can be done. And that's how we study large molecules. In fact, that's how the double helix shape was worked out. I'm sure you may or may have not heard the story. Everybody should know who got the Nobel Prize for the double helix. That was Francis and Crick and Maurice Wilkins. But there was really a lady, Rosalind Franklin. And the stories, it's, one of the stories out of science is that actually I forget which one wrote an autobiography, but said the same thing. She should have gotten the Nobel Prize with them, but basically they were working on the structure, sort of both being more theoretical. Dr. Franklin did X-ray crystallography, and she had taken what she thought was DNA and taken X-ray pictures of it. But she would, there was a race to figure out what the structure is, so she didn't really want to share. So what these two guys did is they went into her lab when she wasn't there and talked her assistant into letting them see the pictures. And then later they published, they were the ones that worked out the double helix shape, and they published it, didn't really accredit her for it. So she didn't get included in the Nobel Prize. So that was one of the dark spots. And I think it was Crick who wrote about it later, apparently felt pretty bad about that. But that's X-ray crystallography, and that's how you study the structure of large proteins, etc. All right, well, that'll be the last in this particular section. I think there'll be one more lecture that we have on another wave topic that doesn't necessarily deal with interference, but it deals with the wave nature of light. So, and I'll see you in the next video.